Welcome to day 12 of the 2023 Advent of Code. So today's problem is hot springs. So scrolling past the story, we have a bunch of springs that might be damaged. No clue what this has to do with hot springs. And the springs are arranged into rows in a giant field outside. For each row, we have condition records that tell us if each spring is optional, operational, in which case it's a dot, or damaged, in which case it's a pound sign. And there are also some springs that are unknown, which are labeled with question marks. There's also some duplicate information on the right-hand side, which tell us the length of each continuous group of damaged springs, and they're listed in order from left to right in groups. And the groups will always be separated by at least one dot, so basically we won't have 4 consecutive springs labeled as 2 and 2. So here's an example of some situations without any unknown spring conditions, and then here it is with some of them replaced with unknowns. And so in the first line, we can see that there is only one way to make this configuration valid, which is to have a damaged spring in the first and third positions, but not the second. No other possible arrangement of these unknown springs would result in the grouping 1, 1, 3. If you're familiar with nonograms, you'll probably understand roughly what this is getting at. If you don't, I would recommend you look it up. It's a pretty fun game. And so, given this information, we want to figure out how many different possible arrangements of operational and broken springs fit the criteria. And so in the second line, we get a more interesting scenario. This spring must be damaged to fit the 3 group, but either of these springs could be damaged, and either of these strings could be damaged. So that gives us 4 possible arrangements. And the last line here actually has 10 possible arrangements. This line here. So the first one must be operational, of course, and then this one also must be operational. But out of these remaining ones, there are 10 different ways to arrange the 2 and the 1 group. And given this information for each row, we want to find the number of arrangements. What's the sum of the counts? So for each line, the way we're going to do this is we're going to do it recursively. And you could do this building from the bottom up, sort of like dynamic programming. The reason we won't do that is because it's a bit more complicated, because unlike with which one was it? There was one problem that could be done with dynamic. Yeah, unlike day 4, we can't store the values in an array cleanly because there are 3 different conditions. Whether or not we're currently reading a block, what the current string is, like the position within the string is, and what the current number configuration is. So that's a lot of axes, and so doing this via dynamic programming would require a kind of confusing data storage format. So instead we're going to do this recursively because it's simpler and efficient enough in this case. So we're going to get the configuration and the nums by splitting the line along the space in the middle. And then we can say nums equals list map int over nums.split on the comma. And so now if we print out CFG and nums together, we see that this is what we get, a string and an array of integers. So now we just define a function that will count the number of valid states given a configuration and a numbers array. And so we can just create a total variable here and then just do total plus equals count of CFG and nums. Okay, so how do we do this count function? We're actually going to want to add one extra variable, whether or not we're currently reading a block. So basically what that flag will tell us is whether or not the previous state that recursively called this instance of the function is expecting us to still be within a block. And so we can call that flag, which will start out initially as false, which means that we're not currently in the middle of a block at the start. So there are a couple of base cases that we want to establish. If the configuration is an empty string, then we must have reached the end, and so nums should not expect any more broken springs. So return 1 if the sum of nums is 0, otherwise we return 0. So this base case just tells us that if we have an empty configuration, then if we're not expecting any more broken springs, there's exactly one configuration that works, which is to just turn all the question marks into operational springs. Otherwise, if we were still expecting at least one broken spring, then there are no valid scenarios. Likewise, if all of the remaining numbers add up to 0, so if we're not expecting any more springs, then if there's still a pound sign left, then we know that it's an invalid configuration, and so we return a count of 0. Otherwise, we return a count of 1, which is just to replace all the question marks with dots. So those are our two base cases. And now, following this, we know that the config is not empty, and we're still expecting more broken springs. So now we can just run an if statement on the first element of the config. So if CFG0 is a pound sign, that means that we've encountered a broken spring. So there is one scenario in which case this is invalid. If the flag is currently true, that means that we are currently reading a block. And if the first number in the run length array is 0, that means that essentially we expect this block to end. So the way we're going to do this is we're going to decrease the first element of nums each time we find a pound sign. And so eventually it will reach 0, which means that the block should be ending here. So if we're in the middle of a block and the block should be ending here, but we see another broken spring, then that means that this block size is invalid, so we return 0. In any other situation, so if we're not currently reading a block, or if we are reading a block but we're still expecting more springs, then we will just pass on to the next index. So we're going to slice CFG by 1 to continue on with the rest of the springs. And then we're going to decrease the first value of nums. But we're not going to mutate it, because if we mutated this array, then we would have multiple references in different locations throughout the call stack, and it might cause issues. So we're not going to mutate it, we're going to construct a new array by taking the first element and subtracting 1, and then inserting the remaining. And so what this star here does is it just takes this array and throws all of the elements flatly into this outer array. So for example, if we have two arrays like this, then if we combine them together like this, we would get a nested array, but if we combine them like this, we would get a flat array. Actually, let me turn this into a tuple, actually. And the reason I'm going to do this is so that we ensure that we cannot mutate it, because mutation would cause issues, and so we're going to make it a tuple just to prevent that from possibly happening. And finally, we're going to set the flag to true because we saw a pound sign, so we're now in a block. If the first item is a dot, that means that we see an operational spring. And so there is one situation in which this is invalid. If the flag is set so we're currently reading a block, and we are still expecting more broken springs in this block, then seeing an operational spring is invalid. In any other situation, we just end the block. And so we just pass on nums as is, and then return and then set the flag to false. And actually, if the first element of nums is 0, that means that we were in a previous block and we expect it to end. So now that we're ending the block here, we want to drop the 0, because the 0 is used as a flag in situations like this to tell us that we are just at the tail end of a block. And so to avoid confusing this thing, we're going to get rid of the 0. So if the first element is a 0, we're going to return all but the first item. And if the first element isn't a 0, then we're fine to continue. Basically, if the first element isn't a 0, it means that we weren't currently in a block, the previous one was also operational, and we're going to continue skipping through operational springs until we meet something else. And if nums 0 is 0, that means that this came right after the end of a block, and so we want to drop this 0 because we no longer need it to guard against this case. In the final situation, the next character is a question mark, which means that it's up to us to decide what the outcome is. So if the flag is currently set, then if the first number is a 0, what that means is we just reached the end of a block and we require that block to end right now. And so the question mark must be a dot, so we have no choice. We're going to get rid of it, and then we're going to, again, do slice off the 0 because we no longer need it to guard against these two cases. And then we're going to set the flag to false because we're no longer looking at a block. Otherwise, if nums0 is not equal to 0, that means that we are currently scanning through a block and we expect this block to continue. So the question mark must be a pound sign. And so in this case, we're going to, again, repeat this construct here to decrease the block size of the first block by 1, and then we're going to keep the flag as true. Otherwise, in this final situation, we aren't currently scanning through a block, and so because we already know from here that we still have more blocks to go, we can either choose to start a block here or we can choose to not. So this is where our recursion branches off. We have two situations. The first is we don't start a block. And so this is the boring case. Nothing really happens here. The second scenario is if we do start a block. And so we'll again repeat this thing to indicate that we've started a block, and we're going to set the flag to true as a result. And so that's basically part 1. Let me recap this because this might be a bit confusing. This part is intuitive, but all of these conditions, what we're essentially doing is CFG is a string at a certain point. This string might not necessarily be one of the lines of our input, it might be the suffix of it. But what we're essentially doing is we're taking a look at the first character in the string, finding whether or not it's valid based on our current state, and if so, we're finding all possible continuations, and then recursing by removing the first element, so we just look at the rest of the string, and then we modify nums and the flag accordingly to keep up the state. Once we've reached the end of the string, we must be sure that we've already satisfied all of the blocks, so the sum of the blocks array must be equal to 0. If we've reached the end of the blocks array, so if we're not expecting any more broken springs, then this is only valid if there are indeed no more broken springs in our configuration. If the first spring is broken, then if we're looking at a block and it just ended, that means that it's invalid because the pound sign must come after another dot to break up the blocks. Otherwise, we just continue on the block by using this here to decrease the first element by 1. If the first spring we see is operational, then if we're looking through a block and we're expecting it to continue having broken springs, then seeing this operational spring is invalid, so we've returned 0. And otherwise, we continue forward. If the first element is 0, meaning that we are guarding against adjacent blocks, then we can chop off the 0 to avoid causing issues. And otherwise we keep the non-zero value and then we set the flag to false. Finally, if we see a question mark, then there are three scenarios really that can happen. If the flag is set so we're currently in a block, then if the block is trying to end, we must end it immediately. And if the block isn't trying to end, we must continue it. So there's a bit of code duplication here, but I think it's fine in this context as it helps with the understanding. Finally, the interesting scenario where we actually branch off in our recursion is if the flag is not set, that means that we're not currently in a block. And therefore, we have two possible outcomes. We can either not start a block and just set the question mark to a dot and skip, or we can start up a block. And another thing that I should clarify that I kind of assumed, but is actually always true based on the way we're doing things, is that if the flag is false, the first block size is never 0. The reason for that is because at the beginning, nums obviously doesn't have any zeros when we first pass it in, and every time we return a false flag, we always chop off any leading 0. So basically that just means that, and in this context, because we're passing nums directly, and the flag is false, we know that nums doesn't have a 0 at the start. Basically, it's important that we consider that case, otherwise we might run into some sort of infinite recursion with cases like this where we keep trying to build blocks because this ends up reaching -1 or something. So I felt that it was important to clarify that every time we set the flag to false, we always make sure to chop off the leading 0, because the leading 0 is only used to indicate that we are currently at a block and it must end. Perhaps it would have been a bit more clear to set that as a second flag, but this is what I ended up having. So that's for part 1. Now for part 2, we see that the spring records were actually folded up. And so to unfold, each spring condition becomes repeated 5 times with a question mark in between. So in other words, we do CFG is question mark dot join CFG repeated 5 times. And then we also replace the list of contiguous groups, so the run lengths, with 5 copies of itself. And so we can just do nums times equals 5. And so if we try this now, it will work, but it took quite a bit of time, and that was a very small input size, so if we try to run this on the full code, it will be very slow. And so this is where I'll introduce the concept of caching. So in our recursion, the reason this takes so long is because we're repeatedly recalculating the same state multiple times. For example, if we have a question mark, if we have 2 question marks, then we'll either have dot pound or pound dot. The remainder of the string will be the same, but we'll need to calculate it twice. Each time we have a duplication like this, it will multiply the number of states by 2, and this very quickly ramps up, exponentially in fact. And so what we're going to do is each time we calculate one of these states, we will remember the result. And if we see the same input into our function again, we're not going to calculate it again. So we'll set cache to a dictionary, and let's surround this in a wrapper. So def inner, we're going to wrap this all in an inner function that will give us the real result. That's not what I meant to do. Okay, and now what we can do is we'll set the key equal to a tuple containing CFG, nums, and flag. Here's another reason why making nums a tuple was important. With Python dictionaries and sets, you can only insert hashable values. What hashable means is that it can take the data and call a one-direction function to get a numerical output. So for example, if I call the hash function on a tuple 1, 2, 3, you'll get this. This number is meaningless, but it's nearly unique for each value. Sometimes you'll get overlap, but it's very rare. You cannot, however, hash a list, and the reason for that is because it's mutable. And if you change the list, the hash value, it causes a bunch of issues, and it's difficult to know what exactly will happen. The reason hashing is used is to make dictionaries efficient. So rather than looking through each key linearly, it looks through it via a hash table. I would recommend you look up how hash tables and hash sets work if you're interested in the optimizations here. But the key takeaway is just that you can't put lists as the keys of a dictionary or lists into a set. And so that's important because cache is going to have a key of CFG, nums, and flag together as a tuple. And so what we can do is if the key is not in the cache, then we'll calculate the value. And then we can just return cache key. And so now if we run it, we see that this runs way faster. It's still not instantaneous, but it's like 2 or 3 seconds. So definitely fast enough. So that's how I do part 2. Basically, it is the same as part 1 if you do it recursively and don't try brute forcing it. And the key part that makes this valid for part 2 is simply just adding a cache. This is known as memoization. It's a strategy often used in recursion to save intermediate values to avoid duplicate computation. So yeah, that's all for today's problem. Thank you for watching, and I hope you enjoyed.